Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on December 4th, 2025, just yesterday. It introduces reward forcing, a method that keeps long videos consistent while restoring vivid motion, and it delivers real-time streaming video generation at 23.1 frames per second on a single H100 graphics card. The paper is titled Reward Forcing, Efficient Streaming Video Generation with Rewarded Distribution Matching Distillation. And as we will see later, the combination of clever memory tokens and reward-weighted training has really impressive implications for fast, high-quality video generation. Figure 1 gives the big picture. Reward forcing makes videos both more lively and more stable while still running in real time at over 23 frames per second. The top bird sequence illustrates enhanced object motion dynamics, where the subject's pose and position evolve naturally instead of freezing. The bottom museum sequence shows immersive scene navigation dynamics, with the camera smoothly traveling through space over a full minute. On the right, the schematic contrasts standard distribution matching with rewarded distribution matching distillation, which pushes the student model's outputs toward regions that a motion quality model rates as having better, more realistic movement. Figure 2 shows how EMA Sync keeps long videos stable without freezing on the first frame. The left panel illustrates basic window attention, which only remembers the most recent tokens, so quality degrades as older frames vanish. The middle panel adds fixed sync tokens from the first frame, which stabilizes attention but causes copied first frame content and stiff motion. The right panel depicts EMA Sync, where a few sync tokens gradually mix in information from evicted frames, so the model preserves long-term history without extra computation. Figure 3 shows how reward forcing runs during streaming text-to-video generation. The left block illustrates the causal student model with EMA Sync, where a few sync tokens in the key value cache keep getting softly updated, so they summarize the whole video history. In the center, incoming noisy tokens are projected into new key value entries for the next frames. On the right, decoded videos pass through a reward function that compares real versus fake style motion, and that reward then reweights the teacher's gradients toward clips with better dynamics. Table 1 makes the performance story very concrete. The proposed model generates short videos both faster and with higher V-bench scores than comparable systems. The main body of the table lists diffusion and autoregressive baselines, which mostly trade off speed against quality. The bottom row for hours shows a small 1.3 billion parameter model that reaches about 23 frames per second, while also topping the chart in total and quality scores. This combination means the method is not just efficient, it also preserves semantic relevance in the generated clips. Table 2 shows that the method keeps long 1-minute videos both more dynamic and more stable than prior systems. The V-bench long columns rate subject and background consistency, motion smoothness, and visual appeal, and the bottom row wins on total score and dynamic degree. Drift here means how much visual quality wobbles over time, so a lower value signals steadier long sequences. The approach achieves the best drift and the highest external QN3 vision language scores at the same time. Alright, the core message is that EMA Sync keeps long streaming videos coherent without freezing on the first frame, and rewarded distribution matching distillation steers the model toward richer, more realistic motion. Together they make high-quality, real-time video generation practical on modest hardware, which really broadens who can deploy these systems. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.